All right, we're going to go over the quiz. First two questions, we're trying to figure out convergence, and there's a bunch of tests. But the go-to test, if we can use it, is the ratio test. And the ratio test says that if the limit as k approaches infinity of the absolute value of consecutive terms is less than 1, it converges. If it's equal to 1, it's inconclusive. And if it's greater than 1, it diverges. So we're going to jump right in. Anytime you see a factorial, ratio test is kind of your go-to. And so if we think about this as the limit as k approaches infinity of the k plus 1th term, it's a little gnarly. It's going to be k plus 1, 9 to the k plus 1, over 2 k plus 1 factorial. And then technically we're dividing by the kth term, but we know when we divide with a fraction, we can multiply by the reciprocal. And the reciprocal would just be the kth term, which is going to look a lot like the original expression, but now we're combining them as kind of a product of fractions. And the way that most of these play out is you usually can simplify things. And so, for example, if we look at the 9s, we have k plus 1 9s on the top and k 9s on the bottom. And the idea is where is there more 9s? You know, if k was 2, for instance, you'd have, you know, a 9 to the 3rd over 9 to the 2nd. Long story short, there's always going to be a 9 left over. When we think about this guy right here, it's really 2k plus 2 factorial. And so remember that if you have 2k plus 2 factorial, you could think of this as 2k plus 2. And then factorials decrease by 1 each time. So you're going to times that by 2k plus 1. You know, I subtracted 1 going from here to here. Times by, subtract another 1. And then when you want to stop, you can put that factorial on there. And so you can really think of this denominator right here as the same as this expression. Meaning that our 2k's with the factorial attached to it is going to cancel out. And so what I believe I have, or my claim, is that the numerator, this becomes a 9, and the k factorials are going to end up just having a 2k plus 2 and a 2k plus 1 with no factorial left on the bottom. So we still haven't taken the limit yet, but we want to know, is this expression going to be less than 1, greater than 1, or equal to 1? And so the tricky thing with most of these, and you'll see it later on in the quiz, is that when you have a constant in here, in this case the constant is 9, that constant isn't really part of the limit. We really want to know what's happening when k goes to infinity. Some people like to pull the constant out and kind of deal with it later. You could still apply the limit to this, but the constant's, you know, carried through. But the idea is if k gets really large, you know, this becomes kind of like 9 over infinity. And we don't usually write 9 over infinity, and you wouldn't want to leave that as an answer. But if you have a 9 over infinity or any constant over infinity, that limit is going to go to 0. Sorry, I'm having some technical issues. And 0 is less than 1, which means this converges. So looking at the second piece here, we'll jump right into it. You know, we got an alternating series. Just to get into it, you know, if you plug in the first couple terms, you'd have -1 over, you know, e. It's going to alternate signs. You know, plug in a 2, you're going to have plus 2 over e squared minus 3 over e cubed plus, and it's going to go on for a while. It's an alternating series, just to get experience with the ratio test, show you that it works. You know, again, if we apply the limit as k approaches infinity of the absolute value, the absolute value of this is just going to turn it into a 1. And so if we look at the k plus 1th term, we'd have k plus 1 over e to the k plus 1. And then we'd have an e to the k over k. And we want to know what is that limit equal to. And the k plus 1 and the k, they don't really cancel out because you know, we have a 1 there. They're going to factor into our limit. But again, going back to the 9s in the first example and the e's in this example, there's one more e on the bottom. You know, if you were thinking about, you know, k as equal to 2, you know, you'd have it e squared over e cubed. There's always going to be, you know, or e to the 4th, e to the 5th. There's always going to be one more on the bottom. And so you can think of this as a, come on, there we go. You can think of this as the limit. Oh my gosh, I'm sorry. There's a learning curve for these things. The limit as k approaches infinity of 1 over e, you know, k plus 1 over k, if I'm grouping them. The 1 over e you can even think of as a constant. It's not affecting the limit. You're really just applying the limit to the k's. And a lot of times the limits are really nice. You know, this limit as k approaches infinity, you can think about L'Hopital's rule, you can think about the leading coefficients. The idea is this limit's equal to 1. And I don't know why I wrote 3 there. We should be an e. And we want to know, you know, is this less than or equal to 1? And it is. 1 over e, you know, it's about 1 over, you know, 2.7-ish. And so this converges because of the ratio test. And it actually has absolute convergence. And so just kind of another fun little piece of advice, when you have an alternating series, if you throw the absolute value bars on it and it still converges, it means that you can apply this idea of absolute convergence. All right, cool. Okay, I'm trying to figure out this technology, so if there's like random gaps, sorry about that. Okay, I'm going to move on to the next couple questions about Taylor polynomials. And these ones are very easy to overthink, but when you have a Taylor polynomial, the thing you want to keep in mind is you want to construct something that has this structure. And so your definition for a Taylor polynomial is you're using derivatives at a point A, and we're given A over here as our coefficients. And I already left off a piece of this. And then you have this structure of, you know, x minus a to the first power, x minus a to the second power, and so on and so forth. That's a 3. You know, x minus a to the third power, all the way to the nth power. And then notice that the derivatives here, you got the second derivative matches up with the exponent, and you also have some factorials to throw in there. And you could apply, you know, a 1 factorial here if you wanted to, and a 0 factorial on the first one, but because those are equal to 1, we usually don't see it show up. And so we want to take this structure and apply it to this function, at a equals 0. So what you need for a lot of these is you need to find, or at least consider, the first, the second, the third derivative, and so forth. So, f of 0, because a is 0, would be e to the negative 0, which is going to be 1. So that means part of our final answer is going to have a 1 right here. F prime of x is negative e to the negative x. So f prime of 0 would be negative e to the 0, which would be negative 1. So that means we're going to have a negative 1 x minus 0. Again, a is 0. F prime of a in this case is f prime of 0, which we found over here. And with e, there's lots of patterns, but we find the second derivative, f double prime of x. We go back to e to the negative x. There's a chain rule in there. And so f double prime of 0 will go back to 1. So this is going to be plus 1 over 2 factorial times x minus 0 squared. And when it says third degree, it says we want to go up to, the term that makes this third degree, which would be the next term. And so similarly, if we apply the third derivative, it's going to go back and forth between 1s and negative 1s. So there's a pattern in there. So we're going to have minus 1 x minus 0 to the third over 3 factorial. So our answer's in front of us. Let's clean it up a little bit. We're going to have 1 minus x, that's this guy, plus x squared over 2 factorial minus x cubed over 3 factorial. And that is the answer, the one I was looking for. Once you have 3 or 4 terms, you could probably continue the pattern. If it was a 4th degree polynomial, you'd start here. You got alternating signs. The test didn't ask you to do this, but if you wanted to write it, in sigma notation, you could think of it as, k approaches 0 to infinity. We got alternating signs, so we'd have something like this to represent that. You got your powers of x, so you have x to the k, and you got your k factorial. I think it looks something like that. All right, let me pause here for a second and readjust it. Okay, we're going to do the same thing for number 4. I'll try to go a little bit quicker. Our function is now an ln function. So we got f of x equals ln of 1 plus x. Our a is 0 still, so it's actually called a Maclaurin series. But let me just find the derivatives real quick, and then we'll plug everything in all at once. So the derivative is going to be 1 over 1 plus x, which you could also think is 1 plus x to the negative 1. I just wrote it like that because the next derivative is easy to find with a power rule. And then the third derivative, which we'll need if we want the third degree, is going to be 2, 1 plus x to the negative 3. And so if we find, f of 0, it would be ln 1. And f prime of 0 would be 1. F double prime of 0 would be negative 1. You can go back and verify these if you want, if you don't trust me. And then the third derivative at 0 would actually be 2. So I'm going to use this formula again. F of 0 in this case, it's usually a, but in this case a is 0. Plus f prime of a, x minus a, plus f double prime of a, x minus a. Again, I should have filled in zeros for these a's. I guess I can fix it. This is a 0, 0, 0, 0. Going back to blue. This is going to be a 2 factorial to the second. And then we got the third derivative at 0, x minus 0 to the third over 3 factorial. I'm going to stop there because that's going to give us our third degree. So if I plug these in, f of 0 was 0, f prime of 0 was 1, f double prime was negative 1, and f triple prime was 2. And so cleaning this up, I'd have 0 plus 1x. I don't know why I didn't plug in a 0 here. Minus x squared over 2 factorial. Plus 2x cubed over 3 factorial. And that is the specific answer to the third degree. Cool. I'm going to pause here and go to the next part.